Hello, everyone. My name is Andrew Fracknoy. I'm the Emeritus Chair of Astronomy at Foothill College in Silicon Valley, and it's my great pleasure to welcome everyone to this special edition of the Silicon Valley Astronomy Lectures. These non-technical talks in astronomy, now in their 21st year, are co-sponsored by four distinguished organizations: the Foothill College Science, Technology, Engineering, and Math Division, the SETI Institute, where SETI stands for the Search for Extraterrestrial Intelligence, the Astronomical Society of the Pacific, and the University of California Observatories, which includes the Lick Observatory. Tonight's speaker in this special program is Dr. Janna Levin, who is Claire Tao Professor of Physics and Astronomy at Columbia University's Barnard College. Her scientific work deals with some of the most exciting topics in modern science: the nature and extent of space and time, black holes and neutron stars, the corpses of stars, the background radiation left over from the early universe, and gravitational waves. In addition to her scientific work, she's also Director of Sciences at Pioneer Works, an interdisciplinary cultural center in Brooklyn that encourages cooperation between the arts and the sciences. And just recently, she's become editor-in-chief of a new culture magazine called Pioneer Works Broadcast, which brings together art, music, science, and technology. This launched May 6th at pioneerworks.org. She's the author of several best-selling books, including How the Universe Got Its Spots and Black Hole Blues and Other Songs from Outer Space. Her first book of fiction, A Madman Dreams of Turing Machines, won the Penn Prize. Now, her latest popular book is the topic of our discussion tonight, and it's entitled Black Hole Survival Guide. It's published by Knopf and available in many formats. So, ladies and gentlemen, it's a privilege for me to introduce Dr. Janna Levin.
I'm so honored to be invited to do this talk, and I really appreciate everyone tuning in to learn about Black Hole Survival Guide. I want to mention my collaborator in this project, which is the artist Leah Halloran. The book is very special to me because she made more than 20 original artworks for the book. And so it's a beautiful little object. And this painting of hers encapsulates our pilgrimage, what we're going to do today, which is to explore black holes. Here is our ill-fated astronaut falling into a black hole. And while we talk about black holes, I want to first set the scene by establishing a kind of astronomical perspective. So many of you know that the Milky Way galaxy has hundreds of billions of stars. This is not a cartoon. This is actually a digital atlas, meaning every cloud of gas and dust and every star has been placed to the best of our knowledge from observations. And those of you who have been to the Southern Hemisphere may have actually seen the Milky Way in the sky. And you know it cuts this milky rift across the sky, but that's because we live in the Milky Way. We cannot climb out of it. Here we are in this digital atlas, which is really an astronomical map, approaching our solar system, approaching the third rock from the sun. We have never seen the Milky Way from that point of view. We've reconstructed it, and we've reconstructed it from light. Here we are on our little rock, and the furthest object we've ever tossed into the universe is one of the Voyager missions, which only a few years ago broke out of the sun's magnetic influence. It's the first human-made object to go interstellar, and technically it's still really in our backyard. So I want to emphasize that most of what we know about the universe, we know because of light. And light travels to us at that cosmic speed limit. Nothing can travel faster than the speed of light. And it relays to us information about the universe. And here we are. When Einstein first started working, he wasn't sure there were even other galaxies out there. So the universe just keeps getting bigger and vaster. We are not at the center of our galaxy, we are not at the center of our solar system, and we are not at the center of our universe. When we take this astronomical perspective, we can see that not only are there hundreds of billions of stars in the Milky Way, but there are hundreds of billions of galaxies in the observable universe. These are actual galaxies, actual astronomical observations, and as far as the eye can see, there are galaxies. Now, in these galaxies, some billion stars may become black holes. And even more than that, we believe that in each galaxy, there may well be a supermassive black hole at its center. So black holes are plentiful in this observable universe, and yet none of the images I've shown you actually have a black hole in it. And the reason is because this is a pretty accurate portrait of a black hole. Black holes are literally dark. They are dark against a dark sky. If you were this intrepid explorer I showed you earlier, who was venturing near a black hole in space, if there was no other light source, you might not even know that you were infringing on the territory of a black hole. You might not even notice. And so my first tip in the survival guide is to bring a light source, because what you want to see when you go around a black hole is the effects it has on the universe around it. Now, we really want to shuck away some of the misconceptions about black holes today. You know, they're often portrayed as weapons of mass destruction, and actually black holes in their purest form are quite benign and in some sense utterly fundamental. So if you want to explore black holes, you have to kind of have a sort of respect for what they do in the universe. If you were to bring your light source, or you were to illuminate a black hole, you might see something like this. So illuminating a black hole is kind of like casting the shadow of a tree, the way the sun casts the shadow of a tree. It does not exist without another light source. So oftentimes when we talk about seeing black holes or looking at black holes, what we really mean is looking at the shadow cast by a bright source. This painting represents what a black hole would look like if there was a tremendous amount of hot debris and gas orbiting the black hole. And you would see, in some sense, an absence there. You would see, in some sense, nothing. Now, what I really want to emphasize is that people have this impression of black holes as a dense object. People often imagine that you would go up to a black hole and you would find a surface there, and you would knock on that surface and you would find an incredibly dense, collapsed physical object. And if nothing else, I would love if you walked away from this appreciating that black holes are nothing. There's nothing there. Black holes are not really an object at all in some sense. Black holes are more of a place. They're more of a place in space-time. And really, technically, black holes are a space-time. So we're going to pick that apart, how black holes are a shadow, how they're nothing, how there's nothing there, how they're not an object, how they're a place. And to do that, we really should begin with the intuition of space-time. Now, the concept of a curved space-time is challenging. And many people may have seen something like this image, where a massive, heavy object is deforming the shape of space and time around it. And the curved space-time tells objects how to fall. Let me see if I can go back. We'll look at that again. And this intuition seems very challenging and very confusing, but there's a sense in which it's actually quite natural, where you can perform the experiment from the comfort of your couch. Now, space-time isn't painted with the curves. It isn't helpfully illuminated like that. All we really see is things moving. So imagine you're on your couch and you're watching things move. Imagine that you throw baseballs from the vantage of your couch. Baseballs will follow a curved path in space. No matter how you throw them, they will always arc towards the Earth. Now, the Earth isn't touching them, the Earth isn't pulling on them. They're falling freely, essentially in the absence of forces. And this mystery of how they're falling freely in the absence of forces is what leads to the intuition that what they're actually doing is tracing the natural curves in space. That last image I showed you, I actually find a little misleading. I think that this one is more three-dimensional, more natural. The idea is that objects deform the shape of space around them, and everything else falls along the natural curves of space. And if you were to perform this experiment, if you were to go to couches around the Earth from Bangladesh to Australia to Japan, every object you throw would follow a natural curve in space. And if you imagined painting the trajectory of those objects, you would be tracing the natural shape of the curved space. And that intuition is really what led Einstein to pursue this very complicated mathematical description of a curved space-time. I think harder intuitively to imagine is it's not just space that's deformed, but it's also time that's deformed. So as you get closer and closer to an object, your clocks actually begin to run at a different rate relative to somebody far away. And that is a tougher concept to take on, but yet one that we actually observe in reality. Now, the black hole, in some sense, is the most extreme version of this. So here it is, it's 1916. Einstein publishes, finally, after many fits and starts, wrong equations, wrong publications, he finally publishes his general theory of relativity, his theory of curved spacetime. And it's beautiful. It's very mathematical. It's more mathematical than Einstein wanted it to be. He said his own troubles in mathematics were significant. And he gets a letter, this is 1916, so it's World War I. He gets a letter from a friend, Karl Schwarzschild, from the Russian front. Karl Schwarzschild is a 40-something-year-old astronomer. He's already very accomplished, but he enlists in the army to fight in World War I, and he's on the Russian front calculating ballistic trajectories. And between that, he's reading the proceedings of the Prussian Academy of Sciences, as you do. And within a short 6 months, he comes up with this mathematical solution. And it's just a fantasy. It's just his imagination. He says, imagine all of the mass of a star concentrated to a point. He doesn't believe that this is possible. He doesn't believe this exists in reality. He's not saying how you would do such a thing. I mean, after all, it's hard to crush a soda can. He doesn't actually think it's going to happen, but it's just a mathematical idealization, which is very, very useful in physics to think of things as mathematical idealizations. So he imagines all of the mass of a star crushed to a point, and he writes down incredibly beautifully the description of the curved space and time around such a thing. Now, if you were our intrepid explorer or astronaut with a jetpack, and this is one of Leah's paintings, and you were to fall around this space-time, you would be able to turn around, fire your jetpack, and escape. You could safely orbit. You could do lots of things, but as you got closer and closer, you would realize it takes a lot more energy and you have to go a lot faster to escape. Eventually, you would reach a demarcation, an area in this otherwise empty space where all the mass is in front of you, where you would have to travel at the speed of light to escape. And of course, the speed of light is a cosmic limit. Nothing can travel faster than the speed of light. So you would discover that, in fact, you could not escape. Not even light could escape. And that demarcation of this otherwise completely empty space is what we call the event horizon. Now, I really want to emphasize there's nothing there. Space is not painted helpfully with these curves. It would look like that original portrait of just darkness against darkness. But you would find that you could no longer reverse course. You could no longer get back to your space station in a safe orbit around the black hole, to your friend, maybe the astronaut Alice, who's left behind. And And that really is what we mean by the black hole. Now, the event horizon thereby casts a shadow, because if no light can escape the black hole, no light can veer closer, it will be utter darkness against a bright background. It is the shadow of the tree. Now, once you cross the event horizon, there is more in your future. An ill-fated astronaut will find that as they're forced to move forward towards the center of that black hole, that there will be a region, at least predicted by the general theory of relativity, that is of infinite curvature, of infinite deformation of space and time. And that's what people call a singularity. Now, the singularity, weirdly, is not really what we mean by the black hole, because even when Sir Roger Penrose, who recently won the Nobel Prize, and one of the reasons he won the Nobel Prize was for this particular observation, even Sir Roger Penrose, when he wrote his paper in 1965 that inevitably a singularity will form according to the math, he said, I don't believe nature will do that. That if we consider matter forces, if we consider quantum mechanics, which is a very subtle theory, maybe the singularity goes away. So I don't want people to be distracted by the singularity, because what we really mean by the black hole is the event horizon. To some extent, that's the more important part. And I want to emphasize that falling across the event horizon is kind of unspectacular. I mean, after all, there's nothing there. If you're in complete darkness, you don't really see anything. And this description that you'll be torn apart actually really won't happen if you fall across a very big black hole. So that's another survival tip. Fall across as big a black hole as you can find. And I think people find that counterintuitive, but imagine you're standing on a basketball. You really notice the curvature of the basketball. But if you're standing on the earth, you know, people still can't perceive the curvature of the earth with their own eyes. And that's because the bigger it is, the less you actually notice the curves. And similarly with a black hole, the bigger it is, the less you'll notice. And you can fall across and survive, although you will find a very unhappy fate on the interior, as we'll describe. Now, Einstein really believed that nature would protect us from their formation. So he gets this wonderful letter from his friend, Karl Schwarzschild, who unfortunately dies within the year from an infection contracted on the Russian front. And he helps him publish this paper, but he does write him back and argues, you know, how would you do such a crazy thing, like crush a star to a point? And he really suggests that nature would protect us from their formation. And over the subsequent decades, physicists began to realize that, in fact, nature cannot protect us from their formation. And this was work that was delved into by people like Robert Oppenheimer, who were studying nuclear physics. And one of the haunting and beautiful aspects of physics is that it's agnostic. It doesn't care what the application is. So while these physicists were studying thermonuclear explosions with the intention of designing a weapon during World War II, they began to also churn the wheels over whether or not thermonuclear explosions were relevant to the existence of stars. So let's see that again, because it was kind of spectacular. And what Oppenheimer, possibly his most important work in theoretical physics, and I don't believe he ever really lived to know this, was confirmed by observation, but some of his most important work was to understand that the thermonuclear fission in the interior of stars, are basically thermonuclear bombs, is what keeps stars afloat and keeps them bright and radiant. And when they run out of thermonuclear fuel, the heaviest stars will begin to collapse under their own weight. And what you're seeing here was the rebound effect of a very heavy star collapsing under its own weight. And much like the critical mass of a bomb, once it crunches down, it actually ignites a higher energy thermonuclear explosion, the whole star explodes. And if the remnant core is heavy enough, there is nothing that can stop it from collapsing catastrophically, unhindered, under its own weight. And that is really how black holes form in nature. Now, the name black hole wasn't assigned until around 1967, when the great relativist John Archibald Wheeler, who educated the entire first generation of American relativists, said in a lecture, he likened the collapsed dead star to the Cheshire cat. He said the star, like the Cheshire cat, fades from view. One leaves behind only its grin, the other only its gravitational attraction. And then he adds, light and particles go down the black hole. And with that, he foisted, in his very charming way, the term black hole on the lexicon. This was some 4 decades after the original mathematical solution. So by the 60s, people began to believe that black holes actually formed. But now it sounds like I'm contradicting myself. I said black holes are not an object, that if you go up to them, there's no dense star there. And now I'm saying they're dense objects. But I want to clarify that as the star collapses, as the core of this dead star collapses, it gets so dense that the curves in space-time get so strong that eventually you reach that region where not even light can escape. And the event horizon forms around it, almost like an archaeological remnant imprinted in the space-time. But the star can no more sit there at the event horizon than it can expand outward at the speed of light. You can think of space-time as a waterfall rushing inwards there. And the star would have to race outward like a fish swimming upstream against the waterfall. And it cannot do that because nothing can travel faster than the speed of light. And this is what Sir Roger showed early on, which is why he won the Nobel Prize, which is that the star must continue to collapse. It has no other choice. There is no mechanism by which the star can stop its own continued catastrophic collapse. So it leaves the event horizon behind and it leaves it empty. There's nothing there. The star continues to collapse, and then we don't really know what happens. Maybe it genuinely forms a singularity. Maybe it leaves a quantum remnant. Maybe there's more complicated story from string theory. But what we know for sure is that it leaves the event horizon empty behind it. And one way to think of this is if you were an astronaut to try to fall in behind this collapsing star in the newly formed black hole, you would drift across the empty horizon. There's no object there. It's just a place. It's just a space-time. Your friend Alice is back on the space station. Alice thinks that you're traveling towards a point in space, like the center of a sphere. But from your point of view, it's as though time has slowed so much as you march towards the event horizon. Your time is running slower relative to Alice's. And as you fall in, you begin to see that point, the singularity, as in your future. You see it as a place, as a point in time, not a place in space. So you can no more avoid falling in as a star did than you can avoid the next moment in time. Now, to give a sense of scale, imagine the sun became a black hole. Now, the sun is actually not heavy enough to end as a dead star in the form of a black hole. That's not the fate of our sun. Our sun will bloat, it will vaporize the inner planets. It's also not a good story, but it will not form a black hole. It has to be heavier. But if some evil genius came along and figured out how to convert the sun to a black hole, it would look something like this. This is a very accurate mathematical model by the physicist Andrew Hamilton. What I want to impress upon you here is the sun presently is 1.5 million kilometers across. If we wanted to make it a black hole, we'd have to figure out how to make it less than 6 kilometers across. Once you crunched the sun to 6 kilometers, it would continue to collapse, leaving the event horizon behind and leaving this shadow. So when we say how big a black hole is, we really mean how far across is the shadow of the black hole. And the sun would cast a 6-kilometer shadow. Think about how staggeringly small that is. Black holes, the whole point of them is that they're small. They're small for their heft. This black hole, this mass of a sun, would fit inside Manhattan comfortably. So many black holes, a natural size for a black hole is 10 times the mass of the sun. And it's 60 kilometers across. So they're kind of city-sized, these dead stars. Now, what you can see in this mathematical model is that if we had a self-illuminated Earth, because of course there's no longer the sun to light us up, it would look like this. Now, it's not actually deforming the Earth. It's just the path of the light rays traveling along the natural curves in space that create the illusion of this kind of warped lens. Notice you can never hide behind a black hole. And that's because the light will always come around. And so, you know, if you're in some like Battlestar Galactica, don't hide behind the black hole, they can see you. One of the things I want to point out, again, in tips of surviving a black hole is you can safely orbit a black hole. This is one of the misconceptions that everything gets torn apart by black holes. You could be as close as 600 kilometers from this black hole, which is staggeringly close by astronomical measures, and happily orbit. So I would recommend you set up your space station, you put your feet up, you get some popcorn, you perform some experiments, and you can begin to record your field guide. Now, because black holes are so small, this is taken from the Nova special that I hosted called Black Hole Apocalypse, which was aired on PBS. I hope people will enjoy it. I'm going to show it again because it's so beautiful. But what I want to illustrate here is that because black holes are so tiny, I mean, they're city-sized, how would you possibly see such a thing? I believe that people are surprised to find out that humanity saw its first black hole 2 years ago. Over 100 years after they were first proposed. Because how would you see such a tiny object? Imagine in this Milky Way that we just looked at with all of its dust and gas and stars and all of that brightness and luminosity and all of that light. How would you see something emitting no light? Literally a shadow of empty space in a bright galaxy. And it is nearly, but not totally impossible. Human beings are very ingenious in how we think about this. So if you want to be, we'll discuss how to see a black hole in a second, but if you want to be the first person to see a black hole with your actual eyes, you would have to get very, very close, hazardously close. This is, again, a mathematical model of an astronaut orbiting a black hole. This is the point of view of the astronaut. The swirling you're seeing of the light from the Milky Way is because of the deformation of the space-time and the path the light is taking, and this astronaut is orbiting. Right now, the astronaut has crossed the event horizon. There's nothing there, nothing to bump into, no object, it's just a place. And they're falling inside. And what I want to demonstrate here is that the black hole is dark from the outside. It lets nothing out, but it's one way. It can be bright on the inside. In this simulation, all the light from the galaxy as the astronaut falls in behind her and is focused into a bright flash of light. So as you fall into the black hole, it can actually be quite bright for you. And not only that, but you could see the evolution of the entire galaxy, eons passing. You could see if we survived climate change, because the light from the Earth would fall in behind you very rapidly, but if you could slow it down, you could unfold if we managed to get ourselves out of this crisis. So black holes can be bright on the inside. Here is another manifestation of that. This is a view of the Milky Way from inside the event horizon, and the light falling in behind the astronaut gets focused to a point because you're all being crushed inward into a smaller and smaller region, and the light gets focused at you and all of the colors combine to make a kind of big white bright flash of light. I call it like the light at the end of a tunnel in a near-death experience. it's really a total death experience, though. Everyone likes to know how you die in a black hole. We'll get to that. Now, because black holes are dark on the inside, and because the nearest black hole is at least 1,000 light years away, nobody's ever laid eyes on one. So why have you all heard about black holes and been so convinced? Since the 60s, people realized that some of the most high energy phenomena that they were observing in the universe was due to black holes. This is a real astronomical image of a galaxy in the direction of the constellation Hercules. And when you look at this galaxy in a certain waveband, this is the radio, you see tremendous jets, high-powered energy jets bursting out of that galaxy, breaking into the intergalactic medium. That jet is much larger than the entire galaxy in which it lives. And we believe that those jets are powered by a supermassive black hole at the center of that galaxy. The black hole is spinning, so that curved spacetime is actually a vortex. It's like a storm in spacetime. It's twisting up magnetic fields, and it's creating essentially a ray gun of high energy X-rays and gamma rays. So another survival tip is do not get in the way of those jets. Those jets will vaporize anybody and anything. There have actually been observations of jets so powerful that they've punctured a neighboring galaxy and blown a hole in that galaxy. In other words, if there were planets, exoplanets, sentient life emerging on those exoplanets, they would have been vaporized by these jets. And we see these jets both from smaller black holes. Here is an example of, am I running? Let's see, there we go. Here's an example of a smaller black hole that is cannibalizing a neighbor. Again, this one is a cartoon, just to be clear. We cannot see anything like this with a telescope. What we do is infer from the jets and the X-rays coming out of this system the power of a very small, otherwise dark object, and we deduce that it's a black hole. So since the 70s, we have deduced that there are black holes tearing tufts off of their companion star, like tearing off tufts of cotton candy, and it's splattering onto the black hole. Imagine dropping a penny from the Empire State Building. By the time it hits this very tiny target, it's very hot, very high energy, and creating bright jets emanating out of it. So when we say things like we see black holes, up until very recently, this is what we have meant. Here we go. Now, I said black holes, nature thought of a way to make black holes by killing off a few stars, but that's not the only way to make black holes. That's just one way. And so I really want to emphasize a black hole is not synonymous with a dead star. A dead star is just the most natural way we thought of for nature to make them. And in fact, that's what we've observed are these dead stars that have all the properties of a black hole, which is to say that they're heavy and small. That is their characteristic. And they're in a very, very small region. It could be that black holes were formed in the Big Bang. The smallest black hole that we can imagine, again, is heavy and small, would be like a fundamental particle. And to some extent, we think of black holes like fundamental particles because they're so pristine and they're so bare because they're not objects. Actually, black holes to some extent are technically perfect. They have they cannot tolerate imperfections. If I tried to throw Mount Everest into a black hole, the black hole would be deformed for a very short time. And then it would shake off the deformation and settle down to a perfectly empty curved space-time. And so to some extent, black holes are fundamental in the universe, unlike any other object. So the smallest black hole we can imagine would weigh about as much as a little pile of flour that you could hold in your hand. But unlike a pile of flour, which is diffuse and made up of a lot of particles, the black hole would be trillions of times smaller than a proton. So you're concentrating all of that mass in the tiniest region. If we tried to make the Earth a black hole, it would be millimeters across. So what I really want you to walk away with is black holes are small. The Nobel Prize that Sir Roger shared with Andrea Ghez and Reinhard Genzel was because of these astronomical observations. These astronomers observed in the direction of the center of our galaxy in the Milky Way, in the direction of the constellation Sagittarius, from our point of view, they observed stars moving at random around this galactic center, and they realized they're orbiting something very small for its heft. And they deduced, just by looking at the orbits over a period of more than 15 years, that these stars were orbiting a black hole. Now, the mass of this star, of this black hole, is 4 million times the mass of the sun. And this speaks to the fact that killing off stars is not the only way to make a black hole, because we don't know how you make a black hole 4 million times the mass of the sun. Maybe smaller black holes that are dead stars coalesced and made bigger black holes, but we don't really know how that would happen in time. So the universe is 14 billion years old, a little less than that, and we don't know how there's enough time to make black holes 4 million times the mass of the sun. So maybe they formed primordially in the very early universe before there were even stars. Maybe they directly collapsed out of the diffuse primordial soup, the stuffs, but we don't know. And this is a really interesting area of exploration, but we know it's there. Now, that's still not seeing the black hole. You see these stars orbit over the course of more than 15 years, and we see that they're orbiting essentially nothing, but that's not the same as seeing the black hole. And even at 4 million times the mass of the sun, that black hole is less than 20 times the width of the sun. So imagine you look at the sky, and you imagine, don't look at the sun, but imagine you're looking at the sun and you kind of know how big it is on the sky. Imagine 20 times the width of the sun. It's actually more like 17 or 18. So it's small for its heft, only that much wider than the sun, but 4 million times its mass. And now push that 26,000 light years away to the center of our galaxy. We call it Sagittarius A star because it's in the direction of the constellation Sagittarius. And think of how tiny that is. Now, there was this wonderful ambition by the Event Horizon Telescope Project to actually observe such a thing. And how would you observe it? You have to hope it's lit up by the light around it so that the shadow is cast against the bright light. But the challenge was to use a series of telescopes around the globe to link them together, to get them to operate as one big telescope, as though it was taking a snapshot of the sky, like an eye snapshot of the sky, even though it might have taken months to observe and to coordinate the timing and to rebuild the image. And this was the ambition of the Event Horizon Telescope. Now, they liken resolving something that small, that far away, to resolving a piece of fruit on the moon. Or as they said before, it would be like reading the date on a quarter in San Francisco from the distance of New York City. So this was a spectacular achievement, and I hope many people saw this. This is indeed the image of the black hole that was captured by Event Horizon Telescope. I was there at the National Press Club in DC when it was revealed, and to some extent the image was no surprise, because what you're seeing is the bright splattering of debris around the black hole, allowing you to cast the shadow. But it actually was not of our black hole. It was not Sagittarius A star. And this I didn't expect at the reveal. There's always fun when there's a surprise. The surprise was they captured the image of the only other black hole they could possibly have resolved with this collection of instruments. And that was the black hole at the center of a neighboring galaxy. We call the galaxy M87. The M stands for Messier. Messier actually created a catalog of objects he wanted astronomers to avoid because he thought they were unimportant. They were smudges, splotches on the sky. Little did he know that M87 is a very nearby galaxy. It has a black hole at its center that's 6.5 billion times the mass of the sun. It is 55 million light years away. And so you take this solar system sized black hole, incredible mass, and you push it at 55 million light years away, the distance light would travel in 55 million years. And you get an object about the same size that the Event Horizon Telescope could just barely capture. So the big reveal was that the first ever human procured image of a black hole was of our neighboring galaxy, M87. I found it very moving at the time to have this sense of sharing this moment with 1 billion people around the globe, something like 1 billion people internationally, not only scientifically, but just viewers chimed in to realize we're all on this little bit of rock together and we're underneath the sky. And here we were all looking at the oddity that is a black hole together. It was quite a great moment. Now back to our explorer, who decides, if you're not that attached to survival, to actually cross the event horizon. And again, they float across this nothingness, this empty demarcation of space, but they can never fire their jetpacks as much as they try. They will never escape. They will see the light from the galaxy behind them. Maybe they fall into to M87, the biggest black hole they can find, so that they can live maybe almost a year as they fall in. It would be a very stressful existential year, and they're marking their experience as they fall closer and closer to the singularity. Now it is true that inevitably, as you get closer to the center of a black hole, singularity or not, you will be flayed, crushed, your ligaments will be torn apart by the curvature of space-time. There is no doubt that if there is an interior of black hole, that would be your fate. And you would be torn apart, asunder into your fundamental quantum bits. And as they approach the singularity, if it exists, it's as though they would effectively fall out of existence, just cease to be. Now, that's anathema to physicists. That's why physicists don't think that's what actually happens in the interior. Some people have theorized that maybe as you get towards the singularity, you actually end up in a Big Bang singularity, and the universe blows out into a new universe, a whole new ecosystem, and all of your quantum bits and quantum information find new life in a cosmos. And that's not the most modern idea, but there's something gorgeous about the concept of a black hole 60 kilometers across that hides an entire universe on its interior. So the black hole can be bigger on the inside than it is on the outside. It could be city-sized on the outside and as big as a universe on the inside. I liken it to Doctor Who's TARDIS. You know, you go into the little phone booth and he has his gigantic lab inside. The modern ideas about black holes are so profound and so confounding but exciting, because the black hole is not an object, because it is nothingness, because it is fundamental. The black hole is this beautiful terrain on which we are exploring the actual laws of physics. Often in pen on paper, we've had a century of the most exciting discoveries of black holes, like they've been revived astrophysically and astronomically in observation, but also mathematically on paper. They are the terrain on which we are trying to understand the fundamental laws of physics. And they are like nothing else in the universe because of it. Now, this is astronomical image, not a cartoon. It's the Hubble Deep Field. It's a tiny, tiny piece of the sky, a little smaller, a tenth the size of the moon, a little postage stamp on the sky. And there are some 20,000 galaxies, each one of these objects you're observing is a galaxy. Imagine that there are billions of black holes in each of those galaxies. And we very, very reliably estimate that nearly every one of the hundreds of billions of galaxies in the whole observable universe have a supermassive black hole at its core. So black holes are no longer thought to be an extravagance or an oddity. They're actually fundamental to our past. We believe that these jets that the black holes create help sculpt galaxies, help modulate their shape and their size. And we are in orbit around a black hole. We are in orbit around Sagittarius A star. It's a very slow orbit, but we're in orbit around it as surely as we're in orbit around the sun. In the far future, in a few billion years, the Andromeda galaxy with its central black hole, supermassive black hole, will collide with the Milky Way, and our galaxies will merge and create a new, bigger black hole. The whole solar system may stay intact and continue to orbit this new gargantuan black hole. Now, if the expansion of space-time does not rip our galaxy apart, and we don't know if it will, our fate will surely be in a very, very long time. I like to say the future is much longer than the past. We will fall into that supermassive black hole. That will be our fate. And so black holes are actually fundamental to who we are in the universe and our past and our future. And in the end, there really is no escaping black holes. Thank you so much for tuning in.
Well, thank you, Dr. Levin. Let's stop
Thanks,
sharing the
Andy.
screen.
Yes. There you are.
Good. Here we are. So thank you for that exhilarating tour through the universe of black holes. I know that there have been questions, and in a minute, I'm going to introduce Dr. Matthews, who's going to curate the questions that have come in. But I want to begin with a question of my own, taking the privilege of the moderator. You talked a little bit about what happens when you personally fall into a star-sized black hole and that you get torn apart. And I wanted you to expand just a little bit on that. I've heard the term spaghettification used for what happens to your body. And I wonder if you could say a little bit more about what the personal experience would be like.
So I believe the term spaghettification is the fault of my friend Neil deGrasse Tyson, who says he didn't originate the term, but he popularized it. So I want to correct, or not correct, but clarify that if you fall into a black hole 10 times the mass of the sun, you don't have long to live. You have well less than a second to live. So if you want to survive long enough to make note of your experience, to record your experience, even if only for yourself, because the messages will never escape, you want to fall into a black hole 1 trillion times the mass of the sun to elongate your chances. So the bigger the black hole, the longer your journey to the future where you will be crushed to death. So essentially, if you imagine space-time being so strongly curved, it's literally as though one knee is on a different path than the other knee, and they get jammed together. But then your head is feeling a different acceleration than your feet, and so you get stretched apart. So you're literally pummeled. You're flayed. So that's what spaghettification is about. It's about the fact that your feet will notice, like, I'm standing on the earth, and I do not notice that my head is actually a little further away from the earth than my feet. I don't really notice. But if I were very close to the center of a black hole, I would absolutely notice, because it's so extreme, that my feet were being accelerated faster than my head. And that's what leads to this spaghettification. Your ligaments would be torn apart, you would be flayed, you would be blown into your fundamental particles, but then we don't really know what happens. Now, if it's really the general theory of relativity all the way down, your particles will just fall into a cut in space-time and cease to exist, and nobody believes that that's true. Because that's a violation of the laws of physics, is what we fundamentally believe. But these are clues. So some people jump to the assumption that, oh, relativity is wrong. That's not it. Relativity is giving us a clue. Like, I call it like a dying man writing in the sand as to what's next, right? So it's telling us, I'm doing really well at the event horizon. I'm doing really well here. And now I'm not doing so well. And there's something else that's going to take over, like a quantum theory of gravity.
Well, now let me introduce Dr. Jeff Matthews, who's the astronomy professor at Foothill College. And he has the questions that have been coming in, and he's going to ask those questions in sequence. Okay. So, Dr. Matthews.
All right, thank you, Andy. And I would also like to thank you again, Dr. Levin, for coming out and speaking with us. And so I'm actually gonna keep on this trend. There were a lot of questions from the audience asking about spaghettification. And so with multiple emails, specifically using the term and talking about how they think it's a great term. And so, you've talked about sort of large things. So, people being pulled into their component pieces, a little bit gruesome there, but had somebody Tom asked, what about tiny things like electrons or even neutrinos? So if, and you said a little bit there about, do they fall into a rift or what?
Right. Well, it's a good question. And in fact, this is the kind of question that people who are interested in quantum gravity are asking. So if the electron, let's just stick with the electron, is truly fundamental, if the electron really is a point particle and there's nothing smaller than the electron, then presumably it would just fall into this cut in space-time, and that would be terrible. So the modern ideas are actually trying to stop that from happening, or trying to understand what is an alternative to this description of falling into a cut in space-time and ceasing to exist. And so there are suggestions that the electron maybe is not fundamental. Maybe if I look at the electron at its smallest scale, I will realize that it's actually a little loop of string. And this goes back to string theory. And the electron is really just a particular harmonic played on this beautiful loop of string. Then the ideas get really more interesting. So as the electron approaches the event horizon, and it's slowing down from the perspective of Alice, who's back at the International Space Station, maybe the loop of string appears to smear out over the event horizon. Maybe it never really falls in. And so these ideas are called holography in other guises. The idea that maybe the whole interior of the black hole is just a holographic projection of the event horizon surface. So a hologram is a two-dimensional encoding of information that projects a three-dimensional image, but it's not really three-dimensional information. Maybe all of that information is really never falls into the black hole, is really encoded on this two-dimensional horizon, and it projects a holographic image of a three-dimensional object. I mean, holography could take me 3 hours to explain, so forgive my 2-second exposition, but that is really a provocation. So there's some of the greatest minds alive today are trying to understand whether black holes, in some sense, are an illusion of a quantum phenomenon, a holographic illusion. It's very, very deep. And this is what I mean, that they are not just dead stars. They're fundamental. They're a fundamental frontier to understand the most profound aspects of the laws of physics.
Right, like yeah, and like you're saying,
everyone's losing sleep tonight. That's all I really am aiming for here.
Okay, so there was another question. So we've got a question from Violet asking, what would happen if something bigger than a black hole fell through that point of no return of a black hole?
A very good question. It was on my my general relativity exam when I was in graduate school at MIT. So I said, if you throw Mount Everest into a black hole, okay, so I didn't really talk about this in depth, but because of the relativity of space and time, if you're an astronaut, let's call him Bob, and you're falling closer and closer to the black hole and you leave Alice behind, your clocks begin to move out of sync. Alice's clock looks really fast to you. because of the deformation of space-time, and your clock appears to run really slowly. And as you approach the event horizon, it appears to actually freeze. And you can think of it intuitively as just the last light signal you try to send to Alice can't make it out because it would have to travel faster than the speed of light. So to Alice, it looks like you've frozen on the horizon and time has stood still for you. For you, your experience is very conventional. You fall right across. Alice is the crazy one who's aging, who's already come and gone, and all her clones are replacing her to send you signals. But so for a long time, people called them frozen stars because they thought you're never going to, as the star collapses even, it should also freeze from your point of view and never even make a black hole. But what we've realized is that your mass deforms space and time. And so you actually have your own curvature, and you will create a bubble in the event horizon that will swallow you because it's not a perfect black hole, you're deforming it. And your deformation would be like throwing in Mount Everest. It will create a little bubble. It will swallow you in a finite time. And then it will shake off that imperfection in what we call gravitational waves, which were observed a few years ago. Literally waves in the shape of space-time will radiate off and the black hole will settle down to a perfect black hole. Now, we see two black holes collide. We see that happen. We don't see it, sorry. We hear the ringing of the space-time as a result of those two black holes colliding. And they do make a deformed event horizon. It bubbles around both of them. It's completely deformed. And then they spin around each other and they settle down and they radiate all those imperfections and gravitational waves, and they become one quiet, perfect black hole. So that's what happens.
Right, and so you're using hear it as kind of an analogy for this bending and stretching of space.
Yeah, so my previous book called Black Hole Blues was about the ringing of space-time due to the collision of black holes. And I liken the black holes to like mallets on a drum. They're moving around and the drum is space-time and the space-time rings, because if you can curve space-time, the curves follow you around and they move in time and they're like waves on a drum. And even in the vacuum of empty space, if you were floating near enough, it's conceivable your eardrum would ring in response to the squeezing and stretching and deformation of space. You would literally hear it. You would not see it with your eyes, but it's actually in the human auditory range for the black holes that we have recorded colliding is in the human auditory range, the frequency of this shape of space-time. It's crazy.
Oh, wow. So you hinted at something that lines up with the next question here. You're saying that there was this idea that the stars would appear to freeze. And so I have a question from Ron asking, at that moment that the star becomes a black hole, what happens to its heat? So all of the motions that were happening inside the star, what happens to that at the moment?
Yeah, no, that's a really great question. So before Einstein, we just talked about Newton. The only thing that mattered for gravity was mass. Something like heat didn't seem to matter for gravity. But when Einstein reconceived of gravity as a curved space-time, he realized that all forms of energy can deform space-time, even heat. So heat becomes a form of energy. And in the way that energies can be equivalent or can be transferred from one kind of energy to another, any energy that goes into the black hole should be recorded as its mass from afar. So because of this one-way window of the event horizon, I can't know if a black hole was made by light or donkeys or encyclopedias or dark matter or dark energy. I can't know anything. So all I can record is its overall mass, which is basically its cumulative energy, including anything that goes into it, heat, anything that goes into it would imprint archaeologically on the shape of space-time as a mass. Technically, the only things we can know about a black hole are its spin, its mass, and its electric charge. And so those are so all of those things are erasing the details of what went in some sense. So unlike a chair, I can't see details of the history of the black hole. anymore.
Wow. Okay. So then with the yeah. So when you talk about you were talking about the space continuing to stretch, all the way down to the potential singularity. So we have a question coming in saying, do the particles themselves sort of realize that the space is stretching, or do they see like their neighboring particle as, okay, that's that particle has been 1/1000th of a meter away from me? Does it still think, oh, that particle is still 1/1000th of a meter away from me?
Oh, it's an interesting question. I would say it gets pretty complicated because, again, it's kind of, you have to start to account for the mass of the particle or the energy of the particle as well, because the space-time is so strongly curved that the slightest little flick of extra mass, even from your quantum particles, creates like a storm, because it's so strong, the gravity is so strong now. So one of the things that people don't realize is gravity is incredibly weak. I can lift my arm even though the whole earth is pulling on me, with just my little muscles. But when you get to very, very strong gravity, now my mass or my particle's mass will couple so strongly because the gravity is now the space-time is so strongly curved that actually it creates just this mayhem. So it's no longer two simple particles smoothly falling, unaffecting the space-time, as though, now they're changing the space-time as they fall in. And so the experience would be basically of a storm is what I would liken it to. And a little flick creates violence in the very, very center, if it exists, if the center of the black hole exists at all.
Okay, and so then somebody asking about, I think this is asking maybe about what you were saying about curvatures. So somebody asking about how could we fall into a really tiny black hole, like a microscopic black hole made in a laboratory, where the curves.
Yeah. Well, so the smaller the black hole, the more important its quantum properties. And so very, very small black holes will actually, I have to alter my claim that black holes are completely dark. So this is what Stephen Hawking became famous for, is he realized that through a very subtle quantum process, black holes can actually, people say radiate, but nothing's coming from the inside out. Black holes are kind of stealing quantum energy from around them, and they evaporate through a process known as Hawking radiation. Now, the big black holes that exist astronomically, it actually turns out they have, we say their temperature, the temperature at which they radiate is lower the bigger that they are, and the smaller that they are, the hotter and more quantum. So tiny black holes actually will evaporate incredibly quickly. There was some concern that at the Large Hadron Collider, that when we collided nuclei together, that they would create black holes. It was not impossible, it was unlikely, but not impossible. And I guess people were not that reassured when physicists said, they'll evaporate away before they swallow the Earth. So there were actually lawsuits where people tried to get an injunction against the Large Hadron Collider turning on. But indeed, we see particles with that high in energy colliding with the Earth's atmosphere, maybe coming from supernova explosion. And if they create little black holes in the atmosphere, they're not eating the Earth, right? So the idea was that the smaller the black hole, the quicker they evaporate, is the gist. So you can't really fall into a little teeny tiny black hole. It would have to get bigger somehow before evaporating.
Well, that's reassuring. So, okay, so now several people asked questions sort of looking at hypothetical communicating or acting across the event horizon type situations. So I think this one kind of captures a lot of what they're going for in these questions. Why can't you fall through the event horizon of a supermassive black hole with a rope attached to your suit, and then have that be tied to a bigger supermassive black hole over there? Could you then be pulled out, or what would happen?
No, you definitely can. There's different ways to answer this. One would be you'd have to pull the rope faster than the speed of light to get you out. So you're much more likely to tear the rope. Not even likely, it is impossible. So there's no mechanism that we know of that allows anything to travel faster than the speed of light. Now, another way of looking at it, so you would have to pull the rope faster than the speed of light to pull you out, and the rope would, break on the outside. But also, even if you tug the rope, the person far away can't know you tugged it, because that signal would have to propagate on the rope through the atoms of the rope faster than the speed of light, and that can't happen either. So none of those things will happen. But I think a deeper answer is that, let's say you've left Alice behind and you're falling towards a black hole and your time is running more and more slowly, and it appears to sit still on the event horizon, not accounting for your own mass for the sake of argument. It's literally, one way to think of it is that you're rotating space and time, kind of like how my left and right can rotate into each other. You're rotating space and time. And when you get to the horizon, you've rotated it so much that the interior direction of the horizon, I kind of referred to this lightly earlier, that what Alice thinks of as the point in the spatial center, from your perception, is the future. And this is something Sir Roger Penrose showed. He showed that time is rotating so much that the interior direction of the black hole is time for you. So you can no more pull yourself out than you can pull yourself backwards in time. And I think that's the deeper answer. I love that you're spending time thinking about these answers. Jeff, that's great. You're like, I'm going to think about this before I ask the next question.
Well, and this is helping me pick, out of, because we have way more questions than we have time to go through, unless you have another 3 hours. But
should we do one more?
Yeah. Let's go ahead and come up to the end here. So we have a question from Marianne. So an earth sciences student.
Nice.
Asking if you can say a bit more about what your perception of time and space would be around and in the black hole. And so I think I'm going to take this and focus that a little bit on what you were just saying about how now that you have that rotation, right? Do you stop perceiving yourself as moving, or like what? Could you explain more about what it means that now ahead of you is time?
Yeah. I remember when I was a relativity student, I expected to learn about the relativity of space and time, and I was anticipating wrapping my head around some things. I remember being very surprised that your perception of time, whoever you are, is always very ordinary. So even though Alice might see Bob slowing down as he approaches the event horizon, and even though, but Alice also sees Bob's biological clock slow down. If Bob's carrying a potted plant with him, the blooms are taking millennia. And the whole thing is in sync for Bob. So Bob's perception is actually incredibly ordinary. He thinks he drifts across the event horizon in a fraction of a second. He just stepped into the shadow of a tree. Nothing weird happens for him. And that's what's hard for I think people to understand. You bring with you your space, your time is always very, very ordinary. It's Alice who you think is messed up. You think Alice is racing through life, that she's lived and died, that she's watching movies at a ridiculous clip, that she's speaking, really fast, and that her clones are replacing her. But she thinks you're the one who's off. But Alice's experience of time is totally ordinary. And so that's a beautiful and strange concept. Bob can travel to Alice's future by approaching a black hole. He can see what happens to the Earth. He can see what happens to civilization, but he himself has not gotten any more out of life than he would have otherwise.
Well, thank you so much for not just a wonderful talk, but for being willing to field this very diverse group of questions. We want to tell the audience again that the book that Dr. Levin has just written is called Black Hole Survival Guide, where you can see more of the beautiful illustrations that she showed and learn more about this really mind-boggling phenomenon. Thank you, Dr. Levin, for a
Thank
terrific,
you so much.
terrific
Thanks so much.
exploration of this amazing realm of both science and the human mind. We thank you for being part of the Silicon Valley Astronomy Lectures. We invite you at this very same YouTube location to look at the other lectures we've recorded over the years, and we'll see you again at another Silicon Valley Astronomy Lecture.